This is the final lecture in the heat treatment course, and in this particular lecture we will look at some applications of the simple applications on some of the principles that we have learnt in this course. So, the first application that I am going to look at is what is thermomechanically treated reinforcing steel bars, or they are called commercially as simply TMT rebars. And what are these? These are bars which have specific properties and are used for construction of high rise buildings. Now, this was a work of a master's thesis in IIT Kanpur, where we looked at what would be the effect if building caught fire, what would be the effect of the properties of these bars. However, in this lecture we will not look into that, but we will look at how these bars are actually produced and what are the heat treatment principles that become important here. So, here you have these what are called as TMT rebars. These are of various diameters. The particular diameter that we studied was the diameter of 25 mm, which are used for construction of high rise buildings. A typical steel composition for such a bar, for example, it is relatively low carbon, it is 0.17% carbon, and it has some amount of manganese 0.69 or so, and silicon 0.19. So, this is just a composition of the specific batch that we were studying. Now, if I look at the macro structure of this, if I just take an image of a cross section of this, what this has a hardened rim and a soft core. So, I am going to look at what kind of a process was used to produce such a bar, where you have a hardened rim on the outside and a soft core outside. So, you start with a bar of a specific dimension of this particular composition, and this is the process you follow. You austenitize the bar again, so go to high enough temperature that you are in the single phase austenite region of the iron carbon phase diagram, and then this bar is coming out of this furnace at a relatively high speed in a steel mill. It goes through what is called as a quenching box, and hence it gets quenched for a predetermined duration, and we will see why you do not want to quench it continuously, you want to quench it only for a predetermined duration, such that the surface layers form martensite while the interior is still soft. The interior is still in the austenite region. If that happens, so it results in the formation of martensite in the outer region while the inner core is still hot. Now, when it comes out of the quenching box, the cooling is stopped from the surface. The inner core of the material is hot enough that heat transfer takes place to the surface and actually tempers the martensite, and that is what it calls auto tempering. So, you do not have to temper the martensite separately, it is the same continuous process, martensite formation and martensite tempering takes place. So, you end up with a tempered martensite surface which is harder, much harder, and a soft core which is a ferrite perlite core, and hence you get a hard outer region and a soft core, because you do not want the completely hardened region, because if you get completely hardened region, then this material will become very brittle and it will not be usable for structural applications for in construction business. If I look at the tensile properties of such a material, this is the kind of tensile properties you get. You get an yield strength of about 600 megapascals, you get ultimate tensile strength of 670, but you get a very large elongation as well, and this is because of the soft core inside. So, this is the simple process of making this material, and as you can see that in order to get this kind of a structure, hardenability of the steel is going to play an important role. So, and hence you have to know what are the transformation curves, what are the continuously cooled transformation curves for such a steel, so that you can design properly the quenching medium, how long you have to quench, how severely you have to quench, so that you get just the right amount of variation in the microstructure from the center to the core to get this kind of mechanical properties. If you look at the microstructure of this material, along the radius starting let us say from the surface down to the center, you would get, for example, near the surface you will get everything 100% martensite, but auto tempering makes sure that this martensite is tempered. So, this region is tempered martensite, then somewhere in this region you have tempered martensite plus ferrite plus pearlite, and then ultimately if you reach the center you end up with a ferrite pearlite core. So, this is how the microstructure all along the radial direction varies for the steel. Now, if you measured let us say the hardness of the material right from the surface along a particular diameter, then this is the kind of hardness profile you get. So, you have high hardness near the surface at both ends, and you have a low hardness in the center signifying a soft core. Of course, when this work was done, in this work we studied what would be the effect if a building caught fire, how will the microstructure change, and many of the fires can be so severe that all the properties that have been achieved by having a tempered martensite in the surface are lost, and the strength of the material severely goes down in that case. So, in many fires even though the building may look reasonably okay, but you may have actually deteriorated the entire load bearing structure of such a building. This is just showing where the hardness variation is going right from this surface to the core and to the surface back end to the other end. So, this was one example where heat treatment principles can help you design such heat treatment schedules. Now, let me take a very different example. Knowledge of heat treatment can help you in designing low technology stuff as well as high technology related stuff. So, here is one particular case study where we looked at improving the life of horseshoes. You may be aware that horses in India are used for carrying very heavy goods, and these horses are moving on hard surfaces. As a result, the life of the horseshoe which is put on the hoof of the horse, is very poor because this horseshoe wears off very quickly and it falls off, and then therefore, the horseshoe has to be replaced very frequently by the horse owner. So, these horses, just to give you a little bit of an idea, these horses are used in brick kilns, for ferrying pilgrims, for transportation of goods, as well as horses are used also for racing as well as ceremonial horses as well. And this is a example over here of this image showing a horseshoe being nailed to the hoof by nails into the hoof, and the life of the horseshoe is low because they walk on hard and rough surfaces. So, in order to, let us just look at an idea of what is the life of a horseshoe of a typical horse which is being used to carry goods in a typical city in India. It is incredibly low, it is of the order of 7 to 10 days, and hence every week or so the owner will take the horse to a farrier for nailing a new horseshoe, and it may cause, frequent nailing may cause injuries. So, there is a need here for improving the life of the horseshoe to a much longer duration. So, in fact, we did this work in which we tried lots of experiments, and horseshoes were really put on horses and data was measured on the life of the horseshoe. But before that, let us just look at the existing process, the existing thermomechanical process of making a horseshoe. The horseshoe is made by a blacksmith by a traditional technique. You start with first bars of certain kind of steel, and here the bars that you use are bars that are called as sariyas, which are used in many of our construction business. It is essentially a low carbon steel. These bars are heated in the austenite region in a coal fired furnace, as you can see in this image. After that, the rod is taken out of the furnace and forged into the shape of the horseshoe. If one looks at the microstructure of such a material under a microscope, well, I will see ferrite, pearlite kind of structure and small amount of pearlite, because it is a low carbon steel. If I increase the carbon, the amount of pearlite will increase. And as you can see, this is the shape of the pearlite that I have shown earlier, and this is the pearlite layers that you can see very clearly here. Now, what can we do to increase the life of the horseshoe? Well, we have to improve the wear resistance of such a horseshoe, then only we can improve the life. One way of doing it is increase the carbon content so that the amount of pearlite increases. So, that is one. Change the material, increase carbon content of steel instead of 0.2% carbon, which is typically the carbon content of steel of sariya, which is used for making horseshoe, increase it in the range of 0.4 to 0.5% carbon. If you do that, then look at the change in the microstructure. You get lots more pearlite. All these dark regions are indicative of lots more pearlite in such a steel, and pearlite would improve the wear resistance of the steel. In addition, or alternatively, one can make some changes in the process. When we studied this process, we found that this process was producing non-uniform heating, so that in fact the properties all along the horseshoe was wearing, and in fact the horseshoe would wear out at the point where the properties were a minimum. So, what we did to improve the uniformity of the property? Well, we introduced a reheating step, so that once the horseshoe is finally made, it is put back in the furnace and reheated to the austenite region, and then instead of simply cooling in still air, we increased the cooling rate. But we did not increase the cooling rate so drastically that martensite would form. We increased the cooling rate. If you remember the CCC curves that we showed in the last lecture, you increase the cooling rate in such a way that you got much finer pearlite. Now, what would that do to produce much finer pearlite? That would increase the wear resistance of the material, it will increase the strength of the material. So, both of them, increasing the carbon content and changing the process, should improve the life of the horseshoe. Using this, we did the following. We also looked for a material which is easily available for the blacksmith. So, we found some grades that are available commercially, EN8 steel, EN9 steel, which have higher carbon content and which are also available as scrap. With these grades and with the faster cooling rate. Now, how did we improve the cooling rate? Well, we put a fan in front of the hot horseshoe. After reheating, it was dropped in this basket with a fan in front of it to cool it faster, so that you got much finer perlite. Alternatively, another technique was developed in which the horseshoe was put in a graphite powder. Now, graphite powder also produces faster cooling because graphite is a good conductor of heat. And in fact, this was developed as a completely new metallurgical process of rapid cooling, without cooling so drastically that you produce martensite. As a result of all this, if I look at it, this is how carbon is increasing on my x axis. If I go this way, I have 3 different materials. One is Saria here, then I have EN8 and EN9, and carbon is increasing in this direction. How the microstructure would change if I use simply normal still air cooling, how the microstructure would change if I had graphite cooling, how the microstructure will change if I have forced cooling under a fan. Doing this, these were the final results of such a study, where if you notice, for a given material, 2 ranges are given. So, for example, Saria here TMT, normal still air cooling, the range is 5 to 10 days. The same material, the low carbon TMT steel, either forced cooling under a fan or graphite cooling, the life changes from 13 to 17 days. Now, I change the material to one of those EN materials, EN8, EN9, fast either cooling under a fan or graphite cooling, my life changes from 25 to 28 days. So, essentially we are able to increase the life by a factor of 4 by properly adjusting the heat treatment of the manufacturing process of horseshoes. Now, coming to the next case study, which was for the wheels of the coach of trains, coach wheels of trains. Here also we wanted to improve the life of the coach wheel. Also, and now what would be the factors that can improve the life of the coach wheel? So, this is one, the earlier study was a fairly low technology study, this is a much higher technology study. But again, the same principles get applied. In the life of the railway coach wheel, if you look at it, the factors which are important are what kind of a wear resistance it has, what kind of a tensile properties it has, what kind of an impact properties the steel has. If I can increase all these 3, I will end up increasing the life of the railway wheel. So, here again, just to if I look at the tensile properties, the properties I am interested in are yield strength and tensile strength, ductility and toughness. I will measure impact resistance, and I would also measure wear resistance. Now, here if I look at what are the properties of the wheels that are being used, the yield strength of the wheel is of the order of 540 megapascal, the tensile strength is of the order of 900 megapascal, elongation is of the order of 14 to 15%. Just to give you an idea what does this 540 and 900 megapascal mean, if I take a 1 millimeter by 1 millimeter cross section rod, 540 megapascal means it can take a load of 54 kilograms, this 1 millimeter by 1 millimeter rod. 900 megapascal means this rod can take up a load of 90 kilograms. Now, just to give you first a good idea, a brief idea of the how such a wheel is produced. So, you start with ingots like this. These are large steel ingots with the specific composition, and from these ingots you produce these railway wheels. How it is produced? Well, this is a flow chart here. First, this ingots either for the coach or for that matter for the locomotive, the same process is used. You have an ingot of dimensions 650 millimeter in height and 355 millimeter in diameter. They are soaked to a very high temperature so that everything is dissolved and it is 100% austenite, and then it is forged in a hydraulic press so that the final height for the coach, for example, reduces from 650 millimeter to 120 millimeter. So, you get a disc out of this. Then it is followed through other processes. It has to be reheated and then it goes into a rolling mill, followed by dish pressing, that gives you the shape of the wheel. Then it is subjected to cooling to about this temperature and then it is reheated again, so that you get austenite again, and then the wheel is subjected to rim quenching. So, you have a wheel in which this wheel, a hot wheel is placed in a rim quenching apparatus, and there are water sprays all around the wheel, and this wheel is rotating and these water spray the rim. Here again the objective here is to produce a hardened rim, but not so hard that you produce martensite, you produce only fine pearlite, and it is possible because the structure is so large that in order to achieve cooling rates to produce martensite are very difficult. So, you end up getting very fine pearlite on the rim, and then eventually all of this quenching etc. produces a lot of internal stresses. So, it has to be stress relieved. So, this tempering is actually for stress relieving, there is no martensite to temper here, and then finally the wheel goes to the machine shop for final machining. The composition of such a wheel has about 0.5% carbon, then it has certain amount of manganese and certain amount of silicon. So, it is essentially a plain carbon steel. Now, when we looked at this problem and we wanted to improve the life of the wheel in terms of improving its wear resistance, its strength, its impact resistance and all, well, one thing is clear that in fact before you even do this, we also looked at the microstructure. These are typical microstructure of ferrite, pearlite that you get in such materials. Now, one way to simply increase the strength is to increase the carbon content. Well, in fact, increasing the carbon content would be increasing the tensile strength as well as the yield strength, but the elongation will plummet down, ductility will go down. So, this wheel would become hard and brittle. So, increasing carbon is not an option. In fact, we decided to reduce the carbon. Now, when you reduce the carbon, what do you add? Because if you reduce the carbon, the strength goes down, the wear resistance goes down, everything will go down. So, we decided that modify the composition and replace it with a microalloyed steel, and we decided to reduce the carbon and add some amount of vanadium in microalloying quantities to offset the reduction in carbon and get the benefits of microalloying. So, what we did? We first did lab scale experiments. So, we reduced that entire ingot into the lab of dimensions height of 100 mm and diameter of 55 millimeters. And we forced the material in exactly the same way as one would force the wheel in an hydraulic press, forced it from 100 millimeter height to 20 millimeter height, and its diameter increased to 120 millimeter after forging, and it was done after heating it to more than 1200 degrees. After that it was subjected to rim quenching, and this was basically the flow chart in the lab. So, you start with this ingot, you soak it to a high temperature, and then you forge it. So, this forging is taking place here. Finally, it forms a disc, and then we designed an apparatus where you could do rim quenching of this, and this is the final shape one gets of the final product. And then we looked at its microstructure and its properties to determine, under what conditions we get what the type of properties we want. And what are the processing parameters that would be important? Forging start temperature, forging finish temperature, quenching start temperature, water flow rate for quenching, quenching time, and then finally stress relieving through a tempering treatment. One looked at the microstructure at different regions. So, these are basically showing different regions, and essentially in the center you can see it is all reasonably coarse ferrite and pearlite present. Then eventually we came up with certain operating parameters for this, and we went to a production place where wheels are actually produced, and they produced the microalloyed steels to our specification, and these were the processing parameters that were used, and the eventual wheel properties that we obtained was yield strength, which was, if I compare it with the existing composition, then instead of about 540 megapascal as the strength, the yield strength, this strength jumps to about 660 megapascal. Instead of tensile strength being 850 megapascal, it becomes 970 megapascals, and elongation remains roughly same, and in fact the impact strength goes up of such a material, and this has been possible because of adding these microalloying element vanadium. And how does it help us? It helps us in shifting our transformation diagrams to produce much finer microstructure. And if I looked at the wear rate, this is the existing wheel and this is the modified wheel, and you can see that the wear resistance of the modified wheel is much lower than the wear resistance of the existing wheel, simply because one obtained a much finer microstructure, much finer pearlite in the rim. And with this, I have shown you that the principles that we have done in this course can actually be applied to real life problems. With this, I come to a close of this lecture, and in fact come to the close of this course, and I wish you all the best.